Welcome to this exercise session where we will be solving a strain energy problem. For this case, we have a beam and we need to calculate, let me put my cursor here, the total strain energy stored in the beam. This total strain energy is caused by the bending moment and shear force produced by this load case that is applied to the simply supported beam. One important note is that the method that I will be presenting here to calculate the strain energy due to the shear action is different from the one presented in class. It differs a little bit. I thought it was a good opportunity to introduce this method in this example. And finally, as you see in the screen, I will be solving this problem using Python just to facilitate the symbolic calculations needed to get to the total strain energy here. So I have on the right here, and where the cursor is the Python environment, and here on the left is my notebook. So we have the same figure of the beam. So we have 12 kilonewtons applied to a 2-meter beam, and that beam has a cross-section, rectangular cross-section of 25 millimeters in width and 50 millimeters in height. Here on the bottom, there is a form correction factor for shear, and this pertains to the method we're going to use to estimate the strain energy due to shear action. It's the same figure I have here in Notebook and in Python. Then let's say in here I have some imports of the libraries I'm going to be using, and basically I would say that we can start solving the problem. So let's see. First, if we're talking about strain energy stored in the beam, and this is going to be due to bending and shear force, so we need to calculate how much is at shear force and how much is at bending. And to do that, we need to take a step back and calculate all the forces that are going to be applied on the beam when the beam is isolated from its support, meaning that I need to build some sort of free body diagram here, calculate reactions in here, and then start building the shear force diagram, then the bending moment diagram, and then apply the equations to calculate the energy, strain energy for both cases. Then let's go to this part here. Let me move just to put some clarification. So let's call this the support A. This is going to be the support B. Let's call this C. So we know that we need to calculate these reaction forces at A and at B. And also I'm going to write or draw my Cartesian coordinate system. It's going to be something like this. So we're going to have X and Y here. Okay, so first is to find out what are the reaction forces, and then work down to shear forces and then bending moment diagrams, because that's what we need. Basically, well, we don't need the diagrams, we need the equations for shear forces and bending moments. But it would be nice to have those diagrams to see if we are in a good path to solving this example. But let's see. So I'm going to write some code here. I'm going to not write so much comments, but I'm going to write the comments in the code so everybody can see them. So first, what I'm going to do is I need to define some symbols for my symbolic calculation procedure. I will define as symbols, for example, the reactions, the force, this width and height, for example, so I can have everything there. So let me see, is there anything else that I'm missing? I think I'm missing the value for a couple of things. Yeah, I'm missing the value for, I'm going to write them down here. So the Poisson's ratio is going to be 0.3, and the Young modulus, or modulus of elasticity, is going to be 205 gigapascals, like this. Yeah, I think that we have now all the ingredients here. Let me write down, okay, let me write the symbols. I think it would be the case to do here first. Yeah, better. Define the symbols. Well, I'm using Copilot, and that's why it's giving me these nice suggestions, but as a software, I need to audit all of those suggestions that it's giving me. So no, I want to have reaction in A, reaction in B. I want to have the load as P, and the reason I'm going to leave it as P at this point, maybe I can substitute it again right now, right away, but if I want to create some sort of methodology to solve these strain energy problems in Python, I know that to calculate, for example, deflection of beams, we need to differentiate certain quantities, such as the moment with respect to the load. So it's better to keep it as a symbol, even though I know the value at this point. So I need to put the width, the height, and what else? X is going to be important. Yes, X, because our equations for shear force and bending moment are going to depend on X. And then I think it's going to be more than enough. So it's completely there, and I think it's perfect as it is. If there is a need to include any other symbols, I will do it later. Perfect. Now, so let's calculate then the reaction forces. Calculate reaction forces. by saying that all the sum of forces in Y have to be equal to 0. And then if I come to here to notebook, then I know that the forces are going to be just 3 forces. Reaction in A, it's going to be pointing up. Reaction on B is going to be pointing up also, and then the load B. So I'm going to call this Fy, and that's going to be, look at this, Ra plus R, wow, minus B. That is correct. Yeah, but this is the sum of forces in Y, and then I need to say that the force equation, I'm going to call it like that, it's going to be an equation that is that all of this, what I have here, is equal to 0. And actually, if I print out this, run this, I'm going to have, as mentioned, so minus P plus reaction in A plus reaction on B is going to be equal to 0. Awesome. Now, this is not enough. I need now to work with the moments to find out the value of these unknowns. So let's see then. Look at this. Calculate moments about, or let's put moments about A. That's a good point. And I'm going to say that moments about A are going to be equal to what? Well, let me go back to here. So if I'm working at A here, so it's going to be, the reaction on A is not going to create any moment because the line of action of A passes through that point that I'm using as center of moment. Then I'm going to have P at a distance of 500 millimeters, and that's going to be a negative moment that this P force is going to be created. And then reaction B is going to be 2000 millimeters times the reaction on B, positive. So let me write it down here. So it's going to be minus P times, so we're going to have 500 millimeters. So let me write it like 500 millimeters, so in meters, because this is going to, just thinking that I could clean out a little bit more this, but no, let me do it like this. And then plus RP times 2000 millimeters, yes. But then this has to be equal to 0, so I'm going to call moment equation. And yes, that's correct. And then moment equation, if I print this out, it's going to be exactly this, as mentioned here. Now what we need to do, we have a couple of equations, 2 unknowns, so we could solve this system of 2 equations. So solving to find Ra and we put the Rb. So I'm going to have them, let me call it Ra, Rb. So this is what's going to be calling, and then this is going to be solving these 2 equations for Ra and Rb. Yes, and then let me just draw a representation of these to find out how they look like. Look at this. So they are 0.75p for A and 0.25p for B. Yes, so the load, the one with the larger load, is going to be the reaction A. So now I want to find the values for those reactions. Then finding the values for Ra and Rb, and then I know that I need to substitute P by its value using P equal to 12,000 newtons, like that. We go down, and that's going to be then. This is interesting. So is it going to give me? No, I just want to do something differently. This is a nice substitution, but I want to just get the values of all of them right away. So I can Ra is going to be equal to the result I got at the beginning, and then I'm going to substitute P like this. Let me just use this notation because I'm used to this one. So P by 12,000 newtons. That's correct. If I want to keep the way I'm doing it, so this, and then for Rb, it has to be pretty similar, like this, perfect. And then I could display both of these equations in a nice way. So I'm going to display, yes. This is a way, let's see how it goes. And this is a way, let's see how it goes. There you go. So we have Ra equals to 9,000 and Rb equal to 3,000 Newton. Okay, fine. Now what we need to have, well, now having these equations, these reactions, we need to calculate how much is, well, the shear forces acting on the length of the beam. So let me write a piece of code here, a comment saying, okay, now I know that as we are shear force, not diagram, but as we are using a traditional approach to calculate the shear force and bending moment diagrams, I know that I would have to split these beams into parts, meaning I would have to split, if I come back to here, so I would have to split this beam into at least 2 parts, so one part here, and then another part here. So I could call this the section 1, and section 2, if I want to calculate that shear force diagram, I mean, I just make a cut here and I see how much are the reactions here. So, but let's do it. So let's use this instance that we have here. So if I have a piece of beam here, something like this, then I know that here is the support. And this is the cut that I have just done. This is 1, 1. And let me delete this because I'm going to substitute it by the reaction force in A here. And let me give this a title saying that shear force, let's call it function. So this is going to be the first part that I need to make a cut, just for the sake of reviewing this concept, this one here. So when I make this cut, I'm going to have a shear force here, like this, V1. And of course, I'm going to have some certain moment here. I'm going to put it like this, M1. So basically, all the way from support A up to B, just before the application of the load P, this is going to be valid, meaning that the reaction, that the only shear force acting on this section is going to be equal to the reaction on A in magnitude. So let's go. On the shear force, I'm going to call it piecewise function because it's a split function. They're going to have there are points where that function is going to be broken, so it's not continuous. So I'm going to call it that B. Actually, let me do something because this is for this part. Now, what happens with part 2 here? So if I consider that my X, as I've been taking everything, is going to grow from here to here, for example, this is X. And I'm going to have a section here. Try to do it as straight as possible. Section XX. Then in section 2, I'm going to have this case. So I'm going to have a beam, a piece of beam. I'm going to have section 2 applied here, or no, the cut is going to be here. And then I'm going to have, let's keep the same colors here. So I'm going to have the reaction on A. Let me use this A. And then I'm going to have also force P applied here at some point. Then this is going to give me a, by making that cut, that this is going to have, let's put something like this maybe. I don't know. Could be negative, could be positive too. And then I'm going to have another moment here. So these are the two instances that I'm going to have in the beam if I want to create a shear force and bending moment diagram or functions in this case. So let's write down that function. I'm going to call that function V. And then this is going to be, yes, it's going to be a piecewise function. And the first one I'm going to have is that, let me come back here to one node, is this part 1, and this is part 2. So I'm going to have at least 2 pieces in that piecewise function. And this is going to be that, the first one is that it's going to be RA, actually. And that RA, yes, it's going to be for all X smaller than 500 millimeters, which I need to transform into meters. Yeah, that's correct. And then, well, this is giving me all of it. And then in the second part of the function is going to be R minus P, yeah, R minus P, like it is in here, for values less than 2000 millimeters or 2 meters. And then for the rest of the cases, it's going to be 0. I could do something here to constrain these to from 0 to 500 millimeters, but it's going to work like this because we are not going to work with negative X values, so this is important. Then let me display this equation, display. Yes, I think this is going to be okay. Let me see how come. Let me get rid of this because this is not making any sense. Like this, yes. Sorry about this. Let me see. P. Let me substitute here at once because I don't want to have that. So I want to have that bit. Let me see. Yeah, let's leave the P there. Because now what I can have is a. I want now to. It would be nice to plot this shear force diagram to see how it looks like. Get the value of V by substituting P equal to 12D3. So that's going to be V value, and that's going to be take V, and then I'm going to substitute this. That's correct. And let me show this V value here. Yes, I don't want to have these newtons here. We show this, and here it is. Perfect. Now let's plot this. Let's make this. Let's use Python to give us the shear force diagram. Plot. And we're going to use implicit function of, or include function in symbolic Python, that is plot. I said, well, now you need to plot this, and that's going to be from 0 to this, no to this, and then shear force diagram, y level is V. Yeah, let's see how it looks like. There it is. That's exactly how the representation of this. So less than 0.5 meter. So we have now in tons of newtons positive, and then from 0.5 to 2, which is this one here, then we have how much? 3,000 minus 3,000 newtons. Oh, this is nice. This looks nice. We're using Python to give us all of these right away. Awesome. Now let's calculate the bending moment function. Yes, bending moment piecewise function. And we know that the bending moment is going to be the integral of the shear force with respect to x, the length of the beam. So I'm going to call it m, and that's going to be, let me see what Copilot is suggesting me. Well, this is too much. Actually, this is, I shouldn't be writing this completely. So I could write, well, I have a shear force function, and I want to integrate with respect to x, and that's it. So I'm taking this function here, and I'm integrating it with respect to x. Now, as I don't need to work with p, meaning making any partial differentiation, because I'm not going to be calculating any deflections or using the Castigliano theorem, I can just use the value of this, so this one that I have just calculated, to integrate it and then get the bending moment piecewise function. And then I could use display. Yes, so I want to plot this, so let's see how it looks like. There it is. Look at this. I didn't need to do anything by hand. So it was just, look at this. Awesome. So this is for x smallest than this one, and this is for x. Well, actually, it would be from 0.05 onto 2, and then 0 otherwise is required in these cases. And let me check something else. So now that we have this, so this would be, oh, this took this one here. Perfect. Yeah. Awesome. Now let's plot also again. So in the bending moment diagram, also using the plot inbuilt function of SymPy. So let's see, we need to plot m. This is this function from x that varies from 0 to 2 meters, and then the title, labels, everything fine. So let me run it. Look at this. Exactly. So here at 0.5 meters, we have the change in the curve for the bending moment diagrams. And that is awesome. It simplifies this a lot. Also, now that we have found these values for the moments, the only thing left is to calculate strain energy stored in the beam by bending and by shear. And let me go back to notebook, and then there is something like this. So, for example, we write down the equations. Strain energy due to bending is going to be equal to what? Well, we know that U B is going to be equal to what? Well, it's going to be 1 divided by 2 EI, and there's something that is appearing here that I don't have, which is the moment of inertia of the cross section of this beam, and then the integral from 0 to L. Let's remember the class of what? Of the moment square dx, and that is it. So we have the moment function, we have E, but we don't have I. So for a rectangular section, such as this one presented here, so I, here, moment of inertia is going to be, let's talk about moment of inertia of this rectangular section with respect to the centroid of that area. It's going to be 1 divided by 12 times the width times the height to the power of 3. And let's use this equation to calculate the first part of the answer of our problem here. So it's a calculation of the inertia. Let's call it moment inertia of the cross section of the beam. I could just put it like this, and then perfect. So I equals to what? To look at it. Oh my goodness, this is scary. So it already knows what I'm going to do. Let me rewrite. So it's going to be 1 divided by 12 times W times H to the power of 3. Sorry, this is not. And we define as symbols H and W. Awesome. And then if I plot this, let me just for the fun of it display because it doesn't take that much. Yes. Oh, look at this is too much. So we have this. Yeah, this is correct, but the only thing is that it has too many decimals. So I can just put something, if I want to keep this track like this, and then something like this, maybe. There it is. This is 1 divided by 12, and then the other parts, and then, okay. But let me delete this, and let's call I value, and that's going to be equal to I, and then I'm going to substitute what? Let's see the value of W, and W is 25 millimeters, and let's just write it in meters. And then I'm going to have H, which is 50 millimeters. Let's write down into, and then let's call the I value. Yes, and definitely this is going to give me a lot of decimals. Let's see how many decimals it's going to give me. So here we have it. So 2.604, and then this much. And let me just restrict it to this much decimals. There are many ways of writing this. Just bear with me, because just to make it look a little bit better. 3, about 4. Yeah, perfect. Now that I have this, I could calculate the strain energy due to bending. Then I have the formula here written in one note, and I can just write it down like this. So it's going to be 1 divided by 2 times E times I value. But now the question is, do I know how much is E? Do I have it as a? I don't have it as a variable here. E. Then let's just write down here. E equals to, we said that E equals to 205 gigapascals, so that's going to be 205 gigapascals, E 9 pascals. Yeah, pascals. Now, if I want to keep consistency, I could call just value, so we know there is a numeric value here. Value I, we look at the equation here. There it is. And then I need to times the integrate what? The moment equation, yes, the moment equation to the power of 2 to the square, the power of 2, and then in x from 0 to that. Then I can just then display this equation here, or the results. And this is going to be in joules. Let me not use the units at this point. Here. And then again, let me restrict these to 3 decimals. We're about 5. Okay, got it. You could write down anything here, so you could put that is, or just to keep the units newtons, meters, something like this. Was not close. Strange. Great. Now what else? Now that we have found the strain energy due to bending, we need to find here strain energy due to shear action. And for that, the equation for that case, for this modified case using this form correction factor for shear, let me write down then. Strain energy due to shear. It's going to be what? Well, that U, let's call it due to shear, V, because of the shear function. That is then, it's a bit kind of a difference. So this 1 plus Poisson modules, then divided by E times A, which is the area of the whole of the cross section, and then times K, and then times the integral from 0 to L, the whole length of the square of the shear force dx. Just like this. Now, one of the things I need to calculate is the area that I don't have. Well, area is pretty simple. It's just W times H, which is given here. And then the form correction factor for shear of a rectangular cross-section is 1.2. So K is going to be equal to 1.2. And let's just write it down here. So I'm going to have the area first that I don't have. And that's going to be, let me just keep consistency. And then this is going to be this. And then I'm going to say, well, the value is actually going to be the area. And then I'm going to substitute. Yeah, width is 25 millimeters, H is 50 millimeters, that's correct. Then I have K value, I'm just going to write it down directly here. And I have new value, which is the Poisson's ratio value, it's going to be 0.3. And I believe I don't even have it. I do have it as a symbol or not. No, I don't have it as a symbol either. All right, so let's do it. So then shear, strain energy due to shear is going to be equal to what? Well, first, let's write down the first fraction. 1 plus new value, and that's going to be divided by, let me see, is E value times A value, yes, oh my, yes, and then that's the same as this one, and then I need to integrate the shear force function from 0 to 2000, the length, okay? And then display this, yes. So let's have it a go. Oh boy, so there is something missing, and that something missing is that V, but I could use V value. Let me see. Yes. Because if I use the previous one, then it would, let's say, give me a totally different, I would need to use another type of if. Let me just check something. This, because then I could just substitute. Let me see, just for comparison reasons. Oh, sorry about this. Look at this. So I'm missing here K value. There it is. Oh. Yeah, in either way, I could use the other one or this one. It would be the same. Perfect. Now that I have both ones here, so the one due to bending and the one due to the shear force, what I could do is just sum them all, and that's going to be it, basically. And that's going to be the stored energy due to both things, the total strain energy. Very nice tool, I would say, to use Python to help in the symbolic calculation of everything. Pretty convenient. You could have your notes at one side and then use Python to help you with those mechanical operations such as certain integrals or different derivatives or something like that. Perfect. All right, I'm going to close down here. This is perfect. This force diagram is to validate what we did, then the moment diagram to validate what we did, and then at the end we just plugged some values in, write down some operations, and we got the answer we needed. Great. Thanks, and we'll see in the next exercise video. Let's do a couple of more of these. Bye.